Hello and welcome to another very quick PlayBASIC live video. I just wanted to talk about image types. In particular, I'm not talking about compressed image types like things like JPEGs and PNG, bitmap and those things, and even PlayBASIC's own image format, PBI. I want to talk about internally what's happening when we have, or why do we have different types of images and their purpose within our programming. And to get sort of some idea about this, we really have to understand, I guess images can be broken down into two different classifications. We have what's a video image and an FX image, or an AFX, which is an extension of that. Now, if you know something about how computers actually are built, you probably understand this a lot easier than other people. Now, inside your system, doesn't matter what kind of processor you have, what kind of memory you have, what kind of GPU you have, which is the video card, the CPU and motherboard have certain characteristics. Now, the CPU is local to main system memory. So your central processing unit, the main CPU in your computer, the thing that runs programs, has a local bus that can access whatever RAM you've got in your computer. Now, CPUs also have things called caches, lots of different types of caches, in fact. That's also relevant, but not so much in this kind of conversation. Now, the CPU and memory are local to each other. So CPU can fetch data from memory here, easy, and it gets sent back to the CPU, and all things are good. And that speed, that read speed, as well as the writing speed, are pretty much the same. Or for the sake of this conversation, we'll assume those things are the same speed. You can read and write. The CPU can grab data from these RAM chips over here and send data back at the same speed. Not really true, but it'll do for this example. But our video hardware is not actually inside this loop, it's actually external. So to get to the GPU, which is another processor internally with another big chunk of memory inside there, in particular modern systems which have very complicated architectures now, or just in the GPU alone. So when we have an image that's a video image, it gets loaded into system memory here and then gets sent across onto the GPU. Now, the idea of video images is that once they're on the GPU side of the equation, they can be drawn to the screen, which is also stored over here, and manipulated. Your manipulations are quite, well, simple. You can just copy the images around. You can't rotate them. You can't have transparency effects and do those kind of things with them, because PB is set up with what's called direct draw, which is really just a set of rendering features that do hardware accelerated block image transfers, or blitting. Because when PB was built, which is way back in the early 2000s now, the uptake of hardware accelerated 2D wasn't really a thing. It was kind of coming into vogue in early DX9, but PB uses a very old version of Direct Draw 3 for compatibility's sake. The whole idea actually is not really to make flashy high-end games. The idea is really to learn how to do this. But of course, as as things moved along, people wanted to do those effects, so we had to implement some way of doing it. Anyway, so video images end up outside of this circle. They end up outside over here on the GPU. Once they're there, we cannot fetch them at the same speed. We can send the image data across to the GPU at a very high rate, but getting it back is probably about 10 to 20 times slower. Now this is, it really depends upon the system. Some systems, in particular modern systems, can do this much better than older systems, but because PB is designed to support old computers, where this is almost completely, it's not impossible to fetch data from the GPU side, but it's incredibly slow. Probably 20 or 30 times slower than reading normal memory. So you can't even read a full image every frame. It takes I can think of one example where to run an 800 by 600 frame, it was taking at least 10 frames to grab it, and that's a lot of cycles, even though it's the same amount of memory. This is because your video card is actually an external device. The types of adapter, types of card, are better now than what they used to be. And in some systems, we don't even have that architecture at all. We just have a CPU and a GPU pretty much on the motherboard itself. I'm actually using an all-in-one computer here at the moment to make this little recording. So video images live over here. They can be drawn easily, blitted around. In other words, the image can be stamped onto another image, which is what drawing does. But we can't really rotate them or do alpha effects on them, because that requires the CPU to read the data from the GPU, modify it, and send it back, which is impractical for most systems. It's kind of getting better now, but it probably will never be all that fantastic on PCs. These days, you're expected basically to move everything across to the GPU, do everything in shaders, which is another conversation completely. So, okay, video images are loaded onto your video card, and then the idea is we never really try and modify them. We just kind of let them go. We just draw them wherever we need them, but we're kind of limited to what kind of things we can do with them. The other alternative is, going back here, is our FX or AFX image types. And these are a version of the image that is stored in system memory. Where did that go? The image lives over here. So the processor can grab the data easily, modify it, and manipulate it any way we like. So what we generally do if you want to have rotated images, in particular, is we store them as an FX image. We use the processor to do the translation and then send the data across to the screen over here. As long as we're not reading from the screen, that process is pretty quick. It could be faster, but it's generally pretty quick. That's not going to work if you try and do things like alpha effects or anti-aliasing, sort of people call it, but really it's just alpha channel, which is what the AFX version of these things is. Try and find some. A lot of this stuff's already in the help files, by the way. Up here and about, there's actually some bits and pieces. I'm trying to think where stuff has gone. Oh, they're down here in images. You get what image formats, different permutations. These are actually formats you can load off disk. And the load is it's a fairly old chunk of code, really. Probably will find a new version, a new loader, when we fully move to PBFX. you might have noticed there's different permutations of these load image commands. This came from a conversation early on, actually, which is a bit off topic, but we're asking people, you know, would you rather optional parameters, or would you rather command names that actually said what they're doing? And surprisingly enough, people wanted command names that said what they do. So yeah, so we've kind of got some double up with some of those commands there. Like load image can do the same job. You've got an optional format parameter at the end. It defaults to 1, which is the video image. So that image, when it's loaded, will end up being transferred across to the GPU and stay there. Then you can draw it using the GPU to draw that image onto another image. But you couldn't actually draw the image in video memory back onto something that's in system memory. Then it has to be just copied pixel by pixel back. Where's the help files gone? Oh, I just lost that, have I? Sorry. Back to images. Whole bunch of permutation stuff. Yeah, well, here we're saying that the built-in loader is okay, but formats like PNG, for example, I think a lot of people think that PNG is just one format, but internally it's lots of permutations of how the data is stored, and we don't support loading every permutation. It's just crazy. Same as JPEG. We support sort of the common case JPEG, but there are actually lots of other newer permutations that it probably won't load. Same goes for bitmaps, by the way, and TGA. We don't support every version of those. Just some common ones. If you want to load lots of different formats, you can use the free image library, which we supply anyway. You just include the functionality. PBI is our own internal image format, which was added recently. Alright. Trying to get back on course here. So we've got these two different sort of categories. We've got images that are loaded and stored in video memory, which are referred to video images, and images that are managed and loaded into just system memory and live over here in system memory. So the CPU has very fast read-write access to them. You can use alpha effects in general, and all you're bound by really is how fast that processor you have is, and how fast the RAM is, by the way, too. It makes a big difference. So generally, probably the best rule I can give you, I think it's actually in the bottom of this article down here. Yeah, it's in here somewhere. Okay, so crash course in sprite draw modes. When we try to do these kind of sprite effects, there's a whole bunch of them in here. I've got some animated things in here about what each effect is doing. Now, effects that manipulate any one of these effects here that manipulates the pixels of the image is going to perform poorly when the image is stored in video memory, because the CPU is doing that modification. It can't fetch the data from that video card at the same speed as it can over here. So what we want to do is we want to have, if you need an image that has to be rotated, then it needs to be an AFX or an FX or AFX image. Simple as that. If we're doing blending effects, we're taking the pixels in the source image and then blending them with whatever we're drawing over. The same thing applies. If you take a sprite image here, like that ship image we're just looking at, so if you're trying to draw this image here to the screen which is in video memory over here, the way blending works is that the source pixel is drawn and a little algorithm is run to blend the source pixel with the destination pixel. So to get the destination pixel, you have to read it from video memory, pull it back to here, do the blending, and then send it back. Generally very slow, painfully slow on some old systems, which is why we don't recommend people doing. It's not that you can't do those effects. You can, because modern CPUs are very fast. Just don't try and do it directly to video memory. Results are going to be very painful, and you'll be banging your head going, oh, why is it so slow? It's not PB that's slow, it's the architecture of the PC. These days, most 2D languages are based around, they're purely hardware accelerated. So you have, they either use OpenGL, which means that everything here is happening on the GPU side, or they use an up-to-date version of Direct 3D. We don't. We use Direct Draw for legacy compatibility reasons. The whole point at the time was that when people started to shift to using Direct 3D to make 2D games, it introduced a whole bunch of problems that didn't exist before. Like you had limits on how big your images could be, because the GPUs only had very small amounts of memory for their textures. And old systems in particular have really tiny GPU caches. They don't have much memory on them at all. So games that you can do easily with Direct Draw, you couldn't do easily with those systems. Sounds crazy, I know, but these days the things have shifted, and obviously the GPU is a much more powerful solution. But with PB, we're still using the classic solution, so your game will run across everything, but it's not really picking out all the hardware acceleration that it could. These days, if you want that, you can use something along the lines of the G2D extension, which is in here somewhere. I was showing the video the other day. It's probably in here somewhere. There's a whole conversation about it on the forums, all that kind of stuff, so it shouldn't be that hard to find. Alright, I've got a bit sidetracked. Getting back to my main point. Okay, we've got two different classifications of images. Video images. When you load image here, give it you're loading some ship image or something. You might put it in slot 1. It will default, if you don't tell it the format, to video. So the load image command creates a chunk of memory on the GPU. So not exactly how it happens, but what actually happens is the file is loaded into memory, the image is decoded, and then sent across to the GPU, and that's where it stays. Right, now that's good for images that you don't want to manipulate. You can do pretty fast image copying with those things. It really just comes down to the system's support of Direct Draw. Windows 10 and Windows 8 aren't particularly that good with it. They tend to sort of have pretty weak emulation. Right. If we need images that we're going to rotate, or we're going to do things like maybe alpha blend over the top of something, or we need alpha channel, those kind of things, then we have to use FX or AFX. Either one. So FX is if you just want an image that you don't have transparencies in, like alpha channel transparencies in, so you just got a single mask color that's transparent. So the image just has two states. You have opaque pixels, which is solid pixels, and the mask color is the color that's being cut out and removed. Whereas AFX, the pixels really have three states. You've got opaque pixels, translucent pixels, or you've got transparent pixels, which just means that when we'll go through the three different states. So in an FX image, or any image actually, FX or video, what happens is that we've got a source pixel, we've got the final pixel here, we'll say, source pixel, and we're kind of checking if the source pixel is, we'll do a very crude sort of basic. So we'll go if source pixel is not mask color, then right pixel. So the idea being is that it scans through the source image and it's looking for this mask color. Any pixel that's not mask color gets drawn to the destination. Other pixels are just not. When we have an AFX situation, we're looking at the alpha channel to work out how this pixel is drawn. If the alpha channel is 255, it just writes the source pixel over destination pixel. If alpha channel is anywhere between 1 and 254, we are blend source pixel and destination pixel. Write result to the destination pixel, or over destination pixel. And if A is 0, then we don't do anything. We just ignore this pixel. So those source pixels have no effect on the destination. The only time that the destination is altered is when the alpha channel is either 255, so it's completely opaque, or when it's translucent. Yeah, hopefully we got through some stuff there. So to load ship, let's say, with an alpha channel, we'd have ship.bitmap. It may be in the slot 2, but we'd give it a format this time. FX format is 2, and I think AFX is 8. I'll just double check that. Yeah, it is. So if we said here, or we could just go do like this. We could go load FX image, and you can see straight away when you read the code through, you don't have to understand any sort of optional parameters. There's also another one to load AFX into image 3. So image 1 would be loaded as a video image. Go back to our picture. The data is loaded into memory. It's decoded. CPU sends it across the GPU, and that's where it lives. So for an FX image, same process is kind of happening, where the image is loaded into memory, it's been decoded, and then the image is created and stored in this memory here. So it means that you want to rotate this image at some point, or scale it, those kind of things, or do some sort of manipulation of that image in the future. And going back to the final one, we've got the AFX image here. Same thing happens. It gets loaded, the file gets loaded into memory, the image is decoded, and the AFX surface is created in system memory here. So if you wanted to draw this onto something else, you would generally have an effect surface in system memory that you're drawing over. So you do all the rendering in Afx Images here in RAM, and then once you're finished, copy that image down across to the GPU to display it. Wow. I hope that's given some sort of clarity on probably one of the most complicated and possibly, well, actually it's one of the most misunderstood things about PV at all. In fact, I don't think I've ever seen anyone who really understands what's going on, which is a shame, because often you'll see people going, oh, why does this work so slowly? Well, you can't fetch that data. They go, oh, I loaded my image and it won't rotate very fast, or it slows the game down so much. And you have a look at the code, and they've loaded the image as a video image, which means that if you try and rotate that, all the rotation effects are done by the processor. So it has to ask video card for the pixels, manipulate them, and then send them back constantly. And that sending them across to the GPU is very fast, but reading them off it is incredibly slow. Just think of, like, probably 10 times, 20 times. On my old Duron test system, it's probably about 35 times slower than writing to video memory, which is why we don't advise ever doing it like that. In the future, we'll probably just go completely OpenGL, and just, we'll still have Afx Images where you can manipulate the images over system memory with the main processor. When you're done with them, you'll send them across as a texture, and then do your compositing stuff on that side, which is pretty much how most games work these days, the modern sort of way of doing it. But those things don't work on old computers. That's why we haven't done that now. You can with G2D. You can sort of mess around and do some really pretty interesting stuff, but it just comes down to what you want to achieve. And if all you want to do is learn how to code, then forget about what it looks like and just get the core mechanics under your belt first, because it doesn't matter how good the rendering solution is if you can't write it. Your idea is just an idea. Okay, I hope that's covered what I wanted to cover, and I'll have to leave it there. I can hear the dog scratching around behind me. Just want to thanks for watching this bit of ramble, and hopefully you pick something up, and I'll catch you some other time. Bye.